Hi everyone, and welcome to questions on haloalkanes. First question we have is asking about Cn- ions reacting with haloalkanes and with carbonyl compounds. We did look at each row and see how it's going to react with each and deciding which one is correct. Now, Cn- ion, a cyanide ion, and that's going to act with a haloalkane as a nucleophile, and it's going to be act as a substitution reaction. It'll kick something out and replace it, essentially. So that leaves us with either C or D. So we've already cancelled out A and B, so it's either C or D. And then with the carbonyl compound, well, again, it will act as a nucleophile yet again, and this time it will be addition. So this is the reason why it is D. So hopefully nice and straightforward. Cn-, it acts as a nucleophile in both senses, so that could only therefore be D. So hopefully nice easy amount to pick up there. Next question, looking at the rate of hydrolysis of haloalkanes. So which statements are true? Well, looking at these here, saying that the rate depends on the strength of the carbon-halogen bond, well, that would be correct. That is a correct statement. That's what it depends upon, not the polarity. That's not something that's particularly important with the rate of hydrolysis of these. So 2 is correct. And then when it says fluoroalkane gives the slowest rate of hydrolysis, that is correct because it takes more energy to overcome to be able to get it to hydrolyze. So 1 and 2 would be correct, so therefore that would be B. Third question, rate hydrolysis, 1 chloropropane and 1 bromopropane. What reagent in aqueous solution should be used? So of those there's only one that we would use because it forms an insoluble precipitate with the selected halide, and that would be silver nitrate. That would be B. Question 4. We have 2 steps here. We have to see what type of reaction is involved. So we have step 1. We have HBr. We have a double bond in the first part there, and then we don't have a double bond. We see bromines in there in the mix, so along with the hydrogen as well. So having a look at that there, okay, then we've got step 2 where we have an OH seemingly has been put in and a bromine has been taken out. So that seems like that's a substitution reaction. So in my eyes here, it's step 2, again, obviously however you want to approach this, but to me, step 2 seems a bit more obvious. So I'd go straight to step 2 and thinking, okay, OH minus, that's going to act as a nucleophile, and that's substituted out the bromine for itself. So I'm looking for nucleophilic substitution in the first instance. Now, if step 2 is nucleophilic substitution, that only leaves us with B or with D. So I've cancelled that down. Now again, if you don't know straight away, cancel things down as best you can. So I'm looking at either for step 1, it's either electrophilic addition or it's nucleophilic addition. So some form of an addition reaction. Well, in this instance here, what would happen first? I know my mechanisms. I know that hydrogen would get bonded first. So that would be an electrophilic addition reaction, and the bromine would then, the second part of the mechanism, when we form the intermediate, the bromine would then go and react with the carbon that has the positive charge. So therefore, that would leave me with B. So again, process of elimination to an extent, then trying to work things out and see what you come up with. And the final question here, we have 1 iodobutane hydrolyzed at a much faster rate than 1 chlorobutane. Which statement explains the different rates? Well, it's sort of, we've touched upon this slightly in previous questions, and the one that, if we look through these, again, try and cancel out the ones that we can't be looking at here. So the bond enthalpy is greater, less polar, we know polarity has nothing to do with it. Bond enthalpy, no, not so much. A greater delta positive charge, and that's not really going to be causing anything to be happening really. So the bond requires less energy to break. Well, that seems why a reaction happening faster is because less energy is required to break that bond, so therefore it can react faster. So I would go with D. Okay, so that will do us for today on questions with haloalkanes. See you next time.